Hello, here's another moments question. We got a uniform ladder of weight W resting with its top against a rough vertical wall and its base on a rough horizontal ground. Right, I haven't given us a picture, so we're going to have to start drawing this as we go along. There's our wall, there's our ground, there's our ladder. It's got weight W. Let's change over to blue for some of these. So we got from the center of the ladder, we got our weight going down. It's a rough vertical wall and rough ground. So we're going to have friction going up the wall. Let's call that F1. And we're going to have friction going left along the ground. We'll call that F2. So they're in those directions. If you think about what would happen, there is no friction. The ladder would slide down the wall and to the right across the ground. So the friction has to be in the opposite direction. So it has to be going up the wall and to the left along the ground, the way I've drawn it. Of course, if you'd drawn the wall on the other side, and then the friction would be in the opposite direction. So the friction has to go towards the wall, I suppose, is the point on this. Coefficient of friction between the wall and the ladder is mu, and between the ground and the ladder is 2 mu. When the ladder is on the point of slipping, the ladder is inclined at an angle theta. Okay, well, I'll just finish the force diagram by adding in these reaction forces. So now we'll call that one an R1, that one an R2. They're our normal reaction forces. And this angle here is theta at the point of slipping. So yeah, point of slipping. So that's going to mean, it must mean that both of the frictions are in this limiting equilibrium, because otherwise it wouldn't be at the point of slipping. You can't have one of them about to go and the other one not. Oh, they're both going to move, or they're not both going to move. So they both must be at limiting point. We have to, I've drawn the diagram. So yeah, that's the first part done. But what else are we going to do apart from draw that? Now we have to find tan theta in terms of mu. So we know we've got a lot of unknowns here. We've got 1, 2, 3, 4, 5 forces. We've got an angle, and then we've got mu. We've got it's two different coefficients of friction, but it's the same unknown as using both of them. So we've got 5 forces, a mu and a theta. So we've got 7 unknowns, but we're leaving 2 of them in our answer. So we're going to need 5 equations in order to be able to figure all this out. So let's get 5 equations. Start with the simple ones. We'll do our F equal mu r. So up against the wall, we've got F1 is going to be equal to mu R1. And then on the ground, we've got F2 is going to be 2 mu R2. So that's 2 equations done. Now we can resolve vertically and horizontally. So let's resolve vertically first. Up arrows, we've got an F1 and an R2. Down arrow, we've got a W. So that's resolving vertically. Resolving horizontally, we've got 2 horizontal arrows. We've got that F2 is equal to R1. So F2 is equal to R1. So that's 4 equations already. So we've only got to do one moment here. Doesn't really matter where we take the moment about. It's going to work whatever we do. So let's try doing, drawing the angle down the bottom. Let's do moments about the touching point on the wall. So we're going to have clockwise moments. We've got an F2 sine theta. So F2 sine theta. I'm not going to bother putting in the length of the ladder, because it's all just going to cancel out, because we've got 2 of them acting at full length and the W acting at half length. So provided we halve the W moment, then everything's going to be fine. So we've got F2 sine theta going clockwise, and then we're going to have W over 2 because it's halfway along the ladder. That's going to be cos theta, isn't it? Along there, that's going to be theta. So we've got W over 2 cos theta. And that is going to be equal to R2 cos theta, because that's also going to be a theta there. So R2 cos theta. So we've got 5 equations, 7 unknowns. So we should be able to reduce this down to having 1 equation with 2 unknowns in. Right, these can be a pain. I mean, I find the best thing to do with these when you've got so many equations is just start eliminating things one at a time. So let's start with this simple one here. F2 is equal to R1. Let's rewrite these and let's just eliminate F2 all the way through. So let's get rid of this F2 here. So, okay, well, that is equal to R1. So F2's been removed. There is no F2 there. This was the one that we're using, and then we can remove that F2, put an R1 there. So now F2 has gone, and we're down to 4 equations, but we've removed one of our unknowns. Let's remove F1 then. F1's quite easy to remove, so we'll use this equation. Where's an F1? Here's an F1. So that W is going to be equal to mu R1 plus R2. So that's removed that one. And we have no other F1, so we've done that one. So that's good. Now let's remove R1. So let's use that equation and we'll remove R1. So here we've got that W is equal to mu R1 plus R2. So I'm going to rewrite that completely so I don't get confused. So now W is going to be 2 mu squared R2 plus R2. So that's rewritten that equation. And then we have an R1 down the bottom. So let's rewrite this one as well. So that's going to be 2 mu R2 sine theta plus W over 2 cos theta is equal to R2 cos theta. That's good. Now let's eliminate W, but I'm going to tidy up this equation a little bit first because it's got a lot going on. Let's divide through by these cos thetas. So let's get rid of that, and make that tan theta. Just makes things a bit easier, doesn't it? And let's multiply through by 2 everywhere. So we get rid of that, put a 2 here, and make that a 4. Now I'm going to replace the W because the W is sitting all on its own. Makes things a lot easier. So what is our equation here? We've got 4 mu R2 tan theta. It's nice that we just got one tan theta sitting around. Now we've got to add on W, which is 2 mu squared R2 plus R2. That's got to equal 2R2. Nice to see we got R2s everywhere, so we can just cancel all of those. Divide everything by R2. That's going to leave a 1 there. We can take that 1 off of the 2 on the other side. So we've now got, rearranging this, I would normally go to another line, but I'm running out of screen. Tan theta is going to be equal to 1 minus 2 mu squared, and then we've got to divide by 4 mu. So if you approach it in a systematic fashion when you've got these multiple equations, I mean, they're not complicated equations, each one on their own. I mean, some of them are really trivial. I mean, here we just got a direct F2 is equal to R1. Check them all off one at a time. Oh yeah, we use that one, and you'll see you can just keep removing them. The danger, I mean, you don't have to do it this way, but if you don't have a sort of consistent approach, a logical approach to it, you can end up going round in circles. So you might end up using, I don't know, the same substitution twice. You might use the same equation twice, and you'll end up getting a 1 equals 1 or something like that, and you won't end up getting the answer that you want. So if you're just consistent of saying, right, let's rearrange to make something the subject. Okay, we didn't have to do much rearranging or any rearranging really here to make them the subject because they were all sitting on their own for the substitutions. But if they were more complicated, rearrange, make something the subject, and then just replace it in every other equation. And then you can say, well, I'm done with that one now. That's gone. That's an equation removed and a variable removed. And just keep chipping away. And if you chip away long enough, you're just left with one thing, which is what we've got here. So yeah, this is an exercise in, well, again, I suppose we've done all of the force stuff. This is our extension on objects in equilibrium. So not just having a point, we've got an extended object in equilibrium. So we've done resolving and we've done the moments. So we've got translational and rotational equilibrium on all of this, and then it becomes an algebra exercise.